Graphene is a 2D crystalline allotrope of carbon, and the discovery of its remarkable properties were discovered by Sir Andrei Geim and Sir Konstantin Novoselov, who were awarded the Nobel Prize in 2010 for groundbreaking experiments regarding graphene. Graphene is ultralight and incredibly flexible, yet immensely tough. It is 100 times stronger than the strongest steel, and it is the thinnest material possible, as well as being transparent. Being so extraordinary in so many ways, graphene has inspired a wide range of uses in subject areas such as electronics, photovoltaics, and water filtration. Graphene is unreal. It's only one atom thick, it's harder than diamond, it's lighter than paper, and it's stronger than steel. In fact, it may absorb 10 times the amount of energy steel can before failing. Graphene is made up of a flat, packed, hexagonal lattice of carbon atoms in a 2D honeycomb-like arrangement. The carbon-carbon bonds give graphene its unbelievably mechanical strength and flexibility. The remarkable properties of graphene have sparked interest in other 2D materials like it. One example is the boronitride analog, more specifically the hexagonal boronitride, because boronitride has two other forms as well. One of the reasons this analog is of interest is its property of being heat and chemically resistant. Additionally, unlike graphene sheets, the hexagonal boronitride acts as a semiconductor because it is a good proton conductor. Another reason that it is like graphene is that there is pi bonding, but the energy levels are too high to allow for good electrical conduction like that found in graphene.
Silicene is another analog of graphene that has recently been explored by scientists, and while it has not yet been proven to exist, predictions have suggested that it would form the shown structure. Silicene sheets would be a major advance in the modern world, as the nano-sized material could easily be incorporated into currently existing silicon computer chips, making them significantly more compact.
So the question becomes, why is there so much interest in these graphene analogs? Perhaps the answer relates to the idea of a band gap, which refers to the energy difference between the top of the valence band and the bottom of the conduction band. Good conductors, such as graphene, have no band gap energies. Semiconductors have slightly higher band gaps, while insulators have the highest band gap energies. By increasing the band gap of graphene, it can be transformed from a conductor to a semiconductor, which has application to technological uses.
So first, let's talk about what is band gap. The band gap is the energy difference between the HOMO and the LUMO level. The HOMO stands for highest occupied molecular orbital, and the LUMO stands for lowest unoccupied molecular orbital. HOMO and LUMO respectively represent two bands, the conduction band at here and the valence band at here. So if electrons are in the conduction band, they can flow freely and thus it will have a higher conductivity. But if most of the electrons are in valence band, they are less freely to flow and result in a lower conductivity. So we would say that in the graphene, if the graphene has no band gap, it will be a good conductor. But if graphene has little band gap, it will be a semiconductor because electrons have to move from valence band to conduction band to be able to move freely. A study has been done on graphene and it shows that if the graphene is wider than 2 nanometer, it acts as a good conductor, which means it has no band gap. However, if the graphene is smaller than 2 nanometer, which is in this case, it will have less conductive because of the non-zero band gap and it will be a good semiconductor. So our project wants to find out the band gap energy difference between the small graphene, we will call it a graphene ribbon, and large graphene, which is called the graphene sheet. Also, we investigate the boron nitride and the silicon analogs of graphene in terms of the band gap energy. So, as we said before, we assign the small graphene as graphene ribbon and large one as the graphene sheet. The graphene ribbon refers to the 1 to 2 nanometer fragments which serve to amplify the semiconductor's character of the molecule. The ribbon has the size of 4 times 12, which means it has 4 rings on the width and 12 rings on the length. The ribbon has the size of 12 times 12. It has 12 rings on every side. Furthermore, The two graphene analogs, the boron nitride and the silicene, both have the size of 6 times 6. The ribbon graphene resembles a realistic 2D particle in a box. It has definite length and width. They have non-zero band gap, and its energy can be calculated using this formula at here. And as we can see that as L increases, the energy difference between the HOMO and LUMO decreases. So the semiconductance character decreases as well. So one of the problems is that how big does graphene need to be for the semiconductance property to be seen? The sheets of graphene, boron nitride, and silicene all have the similar geometry size. So the other question is that which sheet has the highest conductivity?
The band gap energy can be calculated from the HOMO-LUMO energy gap. By calculating the MO diagram for each, we can determine the change in energy between the highest occupied molecular orbital and the lowest unoccupied molecular orbital. After geometry optimization with MOPAC PM6, we calculated the MO diagram using PChem, B3LYP, and PPCVDZ. The structure with the largest band gap would have the largest semiconductive character. As expected, the large graphene sheet had a zero band gap energy between the HOMO and LUMO. This data supports the idea that graphene is a good conductor.
So I use the Heterofolk SCF, more specifically 6-31G model to run this calculation. The molecule is so large, even we use the WebMol long version, the calculation still failed after several days because of the converge failure. The calculation was up to 50 circles and remained constant almost, as we can see from here. And this energy, the last energy should be lower than that of a graphene sheet, because theoretically, band gap of graphene ribbon should be larger than that of a graphene sheet. And we also know that the LUMO energy of both are the same. Thus, the HOMO energy of graphene ribbon should be lower in order to maintain a higher energy gap. And this energy gap is the band gap. And yeah, as I said before, the HOMO energy of graphene ribbon is lower, so the molecular energy of the graphene ribbon should be lower.
First, geometry optimization was done, resulting with the molecule shown. Then the MO diagram was calculated. The energy for the LUMO was negative 0.124 Hartree, or negative 3.364 electron volts. And the energy for the HOMO was negative 0.245 Hartree, or negative 6.667 electron volts. Using the data from the MO diagram, the band gap was calculated to be approximately 3.293 electron volts.
The calculation for the band gap of the silicene sheet was done by optimizing the geometry on WebML, followed by molecular orbital calculations. The highest occupied orbital was found to have an energy of negative 6.528 electron volts, while the lowest unoccupied orbital had an energy of negative 3.75 electron volts. The band gap energy was found to be 2.778 electron volts, and would only increase in size as the sheet is extended. The significant gap suggests that silicene would be a good semiconductor.
From the summary table, it is evident that the boron nitride analog of graphene has the highest band gap energy. This suggests that boron nitride has the highest semiconductance character. Perhaps we will soon see more applications of boron nitride in today's technological world.
The decreasing size of silicon chips used in much of today's technology is quickly coming to its limit. Without the development of new nanomaterials to replace the parts of the circuit within the chip, we will forever be stuck with clunky laptops and TVs. As graphene is an excellent conductor, it is an optimal material for the conductive segments, and the modification of graphene, as well as the search for other nanomaterials, is done in the hopes of discovering a semiconductive material that can be used to complete the theorized nano-sized circuit in future computer chips.